We're getting started on module 5. Is it 5? Yeah. Okay. Okay, then the name of this module is Polyatomic Ions and Molecular Geometry. And in my opinion, there's only one part that's kind of difficult on this deal, and we'll talk about it at the very end. Is that too dark? We can open up the shades a little bit if that's too dark.
I can still see.
Y'all can still see your blanks and everything?
Yeah.
Okay, good. All right, thank you, Elijah. All right, so what is a polyatomic ion? I think this is a blank to fill in. Ions which are formed when a group of atoms gains or loses an electron. So we know what an ion is. An ion has gained a charge by taking on or giving up an electron. Well, we can have a group that does it as well. All right, one of the best examples, I don't know if you have that as far as a blank to put as an example, is sodium hydroxide. The OH stays together as a group, and it's called the hydroxide group. All right, so it looks like this. So we have our sodium that has given away one of its electrons. We know that about sodium. Sodium is eager to give away its one little electron out there in that last valence shell, right? Very eager to give that away. Gives it away to the OH that are going to stay together, giving the OH a negative charge and the sodium a positive charge. So since those take on that negative charge together, we call that a polyatomic ion. And you can see here, if we're looking a little closer, remember they're going to stick together because of those difference in charges. And that is, you know, a fairly strong bond, like a magnet. Not as strong as a covalent bond, but, you know, strong enough because they're going to be very, very attracted to each other because of those charges right there. You can see those unpaired electrons. You saw that here as well, the unpaired electrons. That's going to come into our lecture quite a bit when we get to the geometry portion of this. Okay. Oops. All right. It looks a little bit like this. Once again, when we talk about geometry, see the shape of it? You know, I've shown y'all H2O before. Now we just kind of show it like this, sort of in that bent shape. And we're going to see why we do it that way. Okay, it has to do with those unpaired electrons. It has to do with those bonds right there. All right, so this is a polyatomic ion. That bond right there would be ionic. They're attracted because this is a positive, this is a negative. That bond would be covalent. Okay, so what I'm going to give you now is I'm going to give you a handout. And this is for you to study for next week. You will not be able to use it on the test, the quiz, but it'll be helpful. This is for 2 different parts of our lecture today. So what this chart it does for us here is it gives us a list of the names of these polyatomic ions that tend to pop up now and then. All right, and so you're going to have to learn how to recognize these when you see them in an equation. All right, so this one right here is called carbonate. Notice what is it? CO3, and it tends to take on a -2 charge. Now, do you find that on your chart there? Yeah, carbonate, CO3 with a -2. So remember, we're not going to do anything with that 3 on the CO3, but what are we going to do with that little -2? When we react that with something, we're going to treat it just like the regular ions we worked with before. We're going to crisscross and bring that -2 down to the other side. Remember the crisscross thing? All right, that's what we're going to do with these guys, but it's going to be the whole group, okay, the whole group together. We don't separate those. We have potassium. So when we look at a potassium carbonate, so we're going to take our carbonate, react it with potassium, and I end up with something that looks like that. So there's our carbon in the middle, and our O's right here, and then our potassiums are sticking off the ends right there. So guess what? The potassiums we're taking on 1 plus, 1 plus. That's 2 plus. That gives me an overall neutral group here, right? A molecule that's neutral now. Because these two had a +1, +1. This whole thing had a -2. All right, so then I took that -2 from my CO3, crossed down here to the 2 by the K, get it? And our K is in that group that only has the 1, so it brings down just the 1 over to this side so we don't see it at all, right? So I'll show you how to deal with that. If it's more than 1, what you end up doing is putting that group in a parentheses. All right, so then you know that that group stays together. All right, so that's potassium carbonate. I think maybe were you supposed to draw it or at least just... Oh yeah, it's up there at the top. You were just supposed to draw the bonds between it, I think. I have y'all's book here somewhere. Yeah, just draw those bonds between there. Okay, good. So this is the chart that I handed out to you. All right, there it is. So these are the different groups we'll be looking for. So you'll have to remember sometimes when you see something together, you say, wait a minute. I remember that's a group. So like for instance, we have ammonium, which is NH4 with a +1. Hydroxide, OH with a -1. Chlorate has a -1. Chlorite has a -1. Nitrate, -1. Nitrite, -1. Acetate, -1. So these are all -1s. And over here, cyanide, also a -1. And then I have some bigger ones over here. Carbonate, -2. Chromate, -2. Dichromate, -2. Sulfate, -2. Sulfite, -2. And phosphate, -3. So you might wonder, if I have these things that are different, SO4 and SO3, why are they both -2s? Well, they both happen to have those 2 electrons they want to grab a hold of. Okay, so even though their formula is different, they have that tendency to pull those 2 electrons, each one of those. All right, that's just their characteristic, if you will. You know, if we go through the whole deal of seeing where they are on your periodic chart, and we'll be looking pretty soon at electronegativities and stuff like that. And notice I've added on at the bottom here something called hydronium, H3O with a +1. I don't know if we will encounter that very much. It's just that they wanted me to add that in, so I added that in. Is it on your chart? Yeah, it's on your chart as well. There we go. Okay, so do you remember how to name ionic compounds? So do you have your periodic charts with you? We're going to pull these out. And we're going to remember we put the ITE or the IDE on there, and then but we're going to see here sometimes we're going to put on a different ending because it's on the chart. All right? So normally when we're naming it, we'll put the IDE on there, but if we end it with a group, we might put a different end on it right there. Okay, example 5.1. What is the chemical formula for calcium nitrate? Okay, so hint to you now, nitrate's on our new chart. Let's find it. Nitrate, NO3 with a -1. See it on your chart? Okay, that's a nitrate. And what are we putting? Calcium is in 2A. So what do we know about 2A? +2, yeah. All right, so I'm going to end up doing this. So I'm going to bring that 2 from my calcium, and I'm going to cross over. My NO3 had the 1, right? NO3 had my -1. That's going to cross over to the calcium, so the 1 would be down here, so we don't see it. Notice what I had to do to the NO3. I put it in parentheses, and the 2 goes on the outside of the parentheses. Where did that 2 come from? From the calcium, which is in group 2A. Yeah. So remember when we struggled through that one a couple modules ago, right? So now we need that information. That's one of the things about chemistry is it tends to build on itself, like math, right? You need to understand the previous concept so you can build on it. And so if you remember that, so if you remember also, these ended up kind of being fun as long as you could remember. I let you put those numbers at the top of your charts, right? The one, remember? Yeah, so they're still there. So now all you have to do is add these guys in, but you'll have to remember those, I guess. Yikes, okay. All right, I think we have another one. What about magnesium phosphate? Okay, magnesium is also in group 2A. We can see that on your chart. Right there, I see it. And then what is our new group right here? What is phosphate? Look on your new chart. Oh, wow, cool. See it? Can y'all figure out the equation then for this? Can you figure out the formula that is? Anybody got it? We're going to cross over. Here's one of my numbers. 2. All right, where's that going to go? By my phosphate. What does my phosphate have on it? -3. You see it on the chart? Where is that going to go? We're going to crisscross, y'all. We're going to crisscross. Y'all see it? Who's got it?
MG3 and then parentheses PO4 close parentheses with 3 on the outside.
2 on the outside.
2 on the outside.
Yeah. Yeah. But that's great. That's great. So you got that, and you just got to remember those numbers. Do you see where I got that 3 and that 2, everyone? Who's confused? Anyone confused? Everybody's got this? Okay. So how helpful is your chart on this one? Very helpful, right?
Yes.
Okay. What about copper 1 acetate? I threw one of these in your last quiz, didn't I? I threw one in. Yeah, and so you had to remember that that thing was referring to the copper. So in this particular case, copper is going to have a 1. We don't care plus, minus, we don't care. 1. And then what's our acetate? Isn't our acetate a big one? Yeah, C2H3O2 with a -1. So what's that going to be? That's going to be easy, yeah? Just no numbers underneath. So Cu, then C2H3O2, that's the acetate. Remember those little numbers down there? We didn't have to figure those out. They were already on the chart. That's our polyatomic ion. Is it making sense? You got to think in chemistry, y'all. Anybody taking a foreign language? Does anybody take a foreign language as a course? You know, have you been taking it very long?
Mm-hmm.
Do you know that you get to that day when all of a sudden you start thinking in that language? You know what I'm talking about? Yeah, and sometimes you even dream in that language. You know what I'm talking? So that's when you know, oh man, I got it. Okay, I got it. And you start just thinking in that language. So that's what happens with chemistry. You just got to start thinking in chemistry. And guess what it takes to think in chemistry? Practice, practice, practice. A friend of mine used to say that. Practice, practice, practice. Okay, you got to practice these things. And then you'll say, okay, because that looks really messy, doesn't it? But when we realize this last part here, the C2H3O2 is on our chart, and it's just a polyatomic ion, boom, there it is. We don't have to do anything with that one. In fact, that was the easiest one on the page. It just looks intimidating. But don't let chemistry intimidate you. All right, y'all, it intimidates me too, okay? I used to teach physics to my kids, and some other kids would come to my house and learn physics, and I despise physics. Despise it. I mean, that's not even a strong enough word. If someone could figure out in a foreign language some really, really, crazy word that means you hate it. And I used to, and when I was preparing for it, I was like, why did I agree to do this? Why did I, and so we know what helped me a ton, literally? I talked to God about it. I said, Lord, you made physics. You know how this works. Give me a joy for it. And it started to work. So pray for God to give you a joy for chemistry. Who knows? Then maybe you'll become a chemist and you'll be wealthy. And you'll remember me in your will. That's what I'm hoping for, y'all. Okay? All right, so let's try a new one. Now these are a little bit easier because what we're looking at on the side here, these are all going to be our groupings on our chart. All we're going to do is name them now, okay? And so we're going to start with that front word, and that comes right off your chart. That one happens to be barium. And so look at your chart. What's NO3? Nitrate. So that's just going to be barium nitrate. You see, that's easy. You didn't even really have to remember anything except this whole chart, of course. Yeah, not to be cruel, but yeah. All right, the next one's going to be sodium something. Let's see, what is that weird thing on there? CiO3, or is that ClO3? Yeah, ClO3. So what is it? Sodium chlorate. Yeah. And now we have calcium something. Oh, this is a good one. Calcium, which is in group 2. What is it? Calcium hydroxide. And the last one is lithium. What is CN? Lithium cyanide. Poison. Poison. All right, so lithium cyanide. So that was what? On your own 5.1. Do you have other on your owns in your book? If you sometimes I won't do all the on your owns with you because the on your owns are decided to be done, guess what? on your own. Yeah. So I'm not going to do all of them, but I want to do some of them as good examples for us. Does everybody have those written down? Okay. All right. Give the chemical formula for the following. Now these ones are a little more difficult because we need the chart. Okay. When you have the chart, they're not difficult at all. So potassium sulfate is going to look like what? We do have to do some crossing over. So potassium, where is it? Group 1, yay. Sulfate, what do we have? SO4 minus 2, so it's easy. What's it going to be?
K2SO4.
Yes, K2SO4. And if you wonder, oh no, where'd the 4 come from? It's just right there on the chart. It's that group. It's that group. You didn't have to put that 4 there. That 4 was already there. You get it? That's not a crossover 4. That 4 was already there. Ammonium carbonate. Ooh, wow. Ammonium carbonate. These are both on our list, y'all. Carbonate. Okay, got it? We're going to look at NH4. That's our ammonium. Yes, see it top left? And our carbonate is going to be CO3. So it's going to be NH4 what?
Parentheses
2.
2. And then CO3.
And where's the 2 come from? Look at carbonate on the chart. See the negative 2 up there? Okay, there it is. Boom. And remember those parentheses. Otherwise, it would look like NH42. We don't want that. That's not a real thing. Yeah. Aluminum acetate. Okay, aluminum's on our periodic chart. So that's Al. What group is it in? Over there, 3. And acetate's on our chart, our new chart. C2H3O2 negative 1. Just remember, what's the Al going to be? Because it's in group what?
3.
So we're going to take that 3 over, right?
Yeah.
There it is. There's our Al, there's our big one. And look, parentheses, there's our 3. Where'd our 3 come? From the aluminum. From the aluminum, just crossed right over. Okay? Did you have your grouping written at the top of the chart right there? Yeah. Did the light bulb just come on back there, y'all? You got it? Excellent. I love it. I love it. Okay, yeah, once it comes on, it's not bad at all. The only problem is this chart. Yeah, so I'm considering letting you use it. I'll consider it. Okay, so study it though. Don't not study it because I said that, because I might change my mind.
I'll give you $1.
Okay. Y'all bring me some Starbucks and I'll, no, I'm kidding. All right. Okay, these are fun. So let's just name these. Oh, this is interesting. Look, that's a sulfur at the end right there, so it's going to have a different name ending, right? So what's our NH4? Ammonium, what?
Sulfide.
Who said it? Sulfide, right? Sulfide. Why do we get the IDE? Because it's ionic and it just takes on that name, right? What if you had said ammonium sulfur? I'll give you partial credit for it, but please, sulfide, okay? Because ammonium sulfur isn't anything. It's not anything, all right? Potassium what? Potassium, look at your chart.
Nitrate.
Which one?
Nitrate.
It is nitrate. I was looking at the wrong thing. Okay, potassium nitrate, good. Magnesium something. Ooh, yeah, we see where that 3 and that 2 both come from. Awesome. Magnesium phosphate. Isn't that Epsom salt? That might be Epsom salt you put in your bathtub. Al, so aluminum, what? PO4? That's easy. Yeah, aluminum phosphate. You should probably know. There are some of these I realize are hard, but some of these you should know forever, like ammonium, definitely phosphate, definitely hydroxide. Okay? But cyanide, come on, it's poison. We don't want to remember that one. Okay. All right, have these written down? All right, now we're moving on to what we call molecular geometry. We're still in part A of our lecture right here, but we're going to see now how our bonding, we've been talking about bonding here, those ionic bonds crossing over, that kind of business right there. We're going to see how this bonding actually will influence the shape of our molecules. So when you drew, you remember your Lewis structures you drew out? Everyone loves Lewis structures. No? No hands? Okay. Yeah, Lewis structures. They're all right. We're going to need to remember those again, y'all, and draw some more Lewis structures. But they actually turn out to be really helpful because here's the deal. As far as we know, Like, you know, we've never seen any atoms or any molecules ever. But as far as we know, they're three-dimensional, okay? So you just take my word for that one. That's what they tell us. That's what the experts in the lab coats tell us. So we'll just believe them. And we're going to see what happens. And it turns out when they have these interesting shapes, they tend to act interestingly and similarly to one another. Okay, so covalent compounds are rarely flat. They take on a 3D structure with depth. But you're looking at CH4 in a two-dimensional capacity right there because I'm working on a flat board, right? That's a flat, and when you draw them, you're working on a flat piece of paper. But we want to try to give them depth and show 3 dimensions to them. So this was one way of doing it. All right, kind of strange. Each one of these lines, so over on our left side, each one of those lines, of course, we know represents bonds, right? Those are bonds. And here's the same thing on the right side over here. It's the same thing. Those straight lines are representing shared bonds or bonded ionically, whichever one we're in. This one we happen to be using our covalent. I think we're in covalent, yeah. And so this solid triangle-looking thing is one of the hydrogens coming out at you. And then these dashed line hydrogen thing is one going behind it. So picture it kind of like a tripod. Do you see it if I say it's like a tripod? See, like the tripod on my board right here, one leg is behind, 2 legs are here, and then I have that one actually going up. It's kind of like a tripod. All right, so we are going to get to the theory that proposes all of this, and that theory is called the valence shell electron pair repulsion theory. So you have that at the top of your book. The VSEPR, I'm tempted to say Vesper, but it's VS. VSEPR, but many people do call it Vesper. Valence shell electron pair repulsion theory. So just using those words, let's see if we know what's going on here. We know what the valence shell is, yes? That's that outer shell that has electrons available for chemistry. We know what a pair is. They tend to pair off. And when they're alone out there, there's be like what we call a lone pair, the 2 little dots on our Lewis structures. Repulsion. What charge are all those little electrons? What charge do electrons have? Negative, thank you. Y'all need the coffee is what happened. Okay. All right, they're negative. So I put 2 negative things together. What do? They repel each other, right? They move away from each other, okay? Which is why, if y'all remember from physical science when you learned about the strong force, it's inside the middle of atoms. It's all those positive things all stuck together. How in the world do those positive things all stay together? Well, there's this amazing force called the strong force. And God just said be, and it was. Okay, so there's no other explanation for it, because they should just blow up. They should all repel each other. So these electrons are repelling each other. Okay, so what the VSEPR theory states is that molecules will take a shape so that those electrons can be as far apart as possible. All right, they're going to move as far apart as possible without leaving the molecule. Okay, so they'll become strangely shaped. All right, so our shapes are these, our common molecular shapes. We have one called the tetrahedron. Can y'all see these? They're kind of small. Tetrahedron. And that one I showed you at the beginning, the CH4, is in that shape. Their electrons pushing past each other are going to be at 109 degrees. Now that is some pretty specific math number there. And so I don't know. I just think we're going to get to heaven and say we were totally wrong about this stuff. But this is what we believe right now, okay? That they get pushed to that degree. It makes sense on paper. All right? It makes sense for people who do math. If you were in your math classes, if you prefer geometry over algebra, you might like this. But there's usually 2 groups of math people. Either you love geometry and hate algebra, or you love algebra and hate geometry. So I tend to be on the like geometry side because I can see it. Algebra is too abstract for me. Do you like them both? See, you just make me mad. People like you, not kidding. No. You need to go get a math degree. People who do well in math, go get a math degree. All right, then we have a pyramidal. Some people say it pyramidal. I don't care how you say it. Pyramidal, 107 degrees. An example would be NH3. Bent, 105 degrees. Water is the best example of the H2O. It's beautiful. Trigonal or trigonal, however you want to say that one, 120 degrees, example CH2O. Linear, they're straight across from each other, 180 degrees, CO2's that way. All right, so we're going to go through and look at some of these and see what in the world is going on, okay? And then we'll come to each one, and I think, if I remember right, y'all are supposed to end up drawing these, I think. So, all right, so let's watch this little video.
Chemists use valence shell electron pair repulsion, or VSEPR theory, to account for the shapes of molecules. The theory is based on the idea that like charges repel each other until repulsions are minimized. The like charges in this case are the groups of valence electrons around a central atom in a molecule or ion. We'll represent them as bars attached to a sphere and show the electrostatic repulsions as yellow arrows of varying width. The simplest case has two negative groups around a central atom. At any angle less than 180 degrees, electrostatic repulsions push the bars apart. Repulsions are minimized when the bars attain a linear arrangement. Electron groups can be single bonds, as in gaseous beryllium fluoride, double bonds, as in carbon disulfide, triple bonds, as in hydrogen cyanide, or, as you will see shortly, lone pairs. Three negative groups attached to a central atom attain minimal repulsions in the trigonal planar arrangement, which has an ideal bond angle of 120 degrees.
There's that bond angle.
We observe this angle in molecules with three identical groups, such as boron trifluoride and sulfur trioxide.
We had that on our quiz.
Molecular shape is determined by the positions of atoms, not electron pairs. Therefore, if one of the electron groups is a lone pair, the molecular shape is not trigonal planar, but bent or V-shaped. Since a lone pair is held by only one nucleus, it is less confined in space and exerts greater repulsions on nearby bonding pairs. As a result, the bond angle is less than 120 degrees, as you can see in this model of ozone. Four electron groups around a central atom attain minimal repulsions in a tetrahedral arrangement, which has an ideal bond angle of 109.5 degrees. The tetrahedral shape is very common, especially in organic molecules. An example is methane, the simplest hydrocarbon. With one of the four electron groups a lone pair, the shape is trigonal pyramidal. Since a lone pair exerts greater repulsions than a bonding pair, the bond angle is less than 109.5 degrees. Ammonia is a common molecule with this shape. Its bond angle is 107.3 degrees. When two of the four groups are lone pairs, the molecule has a bent or V shape. Two lone pairs exert greater repulsions than one, so the bond angle is reduced even further. Water, for example, has a bond angle of only 104.5 degrees. Four electron pairs fill the valence level of a period 2 atom, but one from period 3 or higher can use d orbitals to expand its valence level and bond to more than 4 atoms. 5 electron groups minimize repulsions when they point to the corners of a trigonal bipyramid. Here we find two ideal bond angles. Equatorial groups lie 120 degrees apart, and axial groups lie 90 degrees away from equatorial groups. When phosphorus reacts with excess fluorine, the trigonal bipyramidal molecules phosphorus pentafluoride forms. Once again, when lone pairs are present, different shapes result. But a lone pair in an axial position creates 3 strong 90-degree axes.
Okay, just real quick, this right here with this more than 4 is really advanced chemistry. Okay, so it's not, you're not going to know this part. Okay, you're not going to need to know this part. Just to that tetrahedral one you need to know. But let's finish watching it just for the,
ideal
it's interesting.
equatorial repulsions, whereas a lone pair in an equatorial position creates only two 90-degree repulsions. Therefore, to minimize the number of 90-degree repulsions, lone pairs always occupy equatorial positions. As before, lone pair repulsions reduce all other bond angles. With one lone pair, the object has a seesaw shape. Sulfur tetrafluoride is an example.
What's that? D shell has 10.
With two lone pairs,
10
the
electrons.
object is T-shaped, and the two remaining angles are less than the ideal 90 degrees. Bromine trifluoride is a T-shaped molecule. The final shape in the trigonal bipyramidal arrangement occurs when a third equatorial lone pair repels the axial groups to 180 degrees. The object has a linear shape, as in the case of the triiodide ion. The final common arrangement has 6 electron groups attached to the central atom. Repulsions are minimized when the groups point to the corners of an octahedron, and thus lie 90 degrees apart. Sulfur hexafluoride has an octahedral shape. Unlike the trigonal bipyramid, all positions are equivalent in an octahedron. So one lone pair can take any position to give the square pyramidal shape, with all bond angles less than 90 degrees. Iodine pentafluoride has this shape. To minimize repulsions, a second lone pair must lie 180 degrees from the first. The 4 remaining bonding groups are repelled to the ideal 90-degree angle and define the square planar shape. Xenon tetrafluoride, one of the first noble gas compounds to be made, is a square planar molecule.
All right, so if you like the second half of that video right there, you might really enjoy advanced chemistry. All right, so we don't need to know D shells. We're just doing S&P, okay? All right, which one's this? That's our tripod looking thing, right? So that's called tetrahedral. It's 109 degrees. Are y'all supposed to try to draw that? Can you do it? Next week when we get together, we'll make some of these, in little models. All right, so you're just going to draw that, look at, try to make that one look like it's going behind it there. So what do you need to know? You need to know the name of its tetrahedral, and all the angles, bond angles, are at approximately 109 degrees. That's what you need to know. CH4 is a great example of this one. So the next one we're going to look at, we're going to take away that top leg. So imagine that with that top leg gone. And we end up with something that looks like that. And that is called pyramidal, however you want to say it. And what happens is that these get pushed a little bit to 107 degrees. And NH3 is a good example of that. Because that would have an unpaired group of electrons right there at the top, right? And they're going to be pushing down on those little legs a little bit. So you can see how that looks like a little bit like a pyramid, I guess, right? A little bit like a pyramid. Except a pyramid has a square base, so. Yeah. All right. Our next one that you're drawing, we're going to take away another leg, and we end up with that spun right there. That's bent. Yeah, that's H2O. H2O. So, there were a couple of different options for this one, a single lone pair kind of a thing with a double bond, but H2O has 2 unpaired groups up there, so it pushes it. So this is our classic one, so 105 degrees is what we're going with on bent. Okay, so not everyone's going to be right at 105, but we're going to use this as our base. One that only has 1 paired, what did they say, 107 or something like that? We'll go with 105. I think they actually said 104.5, right, in the video? I mean, I'm thinking, boy, they have some really good measuring tools to get that little angle just right. It's all theory, all theory. That's our bent one. That's probably one of the easiest ones to draw, yeah, okay? And our next one is that one. That's easy to draw too, okay? This one is called trigonal. CH2O, so here's our carbon, here's our two H's, and here's our O. That's probably a double bond right there. 1, 2, 3, 4, 5, 6, 7, 8. Right, yeah, 120 degrees. That one's easy to understand. They're just pushed exactly opposite each other, as far as they can get away from each other. And then the easiest one of all comes next, linear. There it is. CO2, 180 degrees. Okay, now we actually are going to take and apply these to some more stuff. So these are rules. This is on the bottom part of your handout right here. In order to find out what shape something is, you're going to follow these rules. You'll see them written right here. First thing you're going to do, boo, we're going to draw the Lewis structure. Yikes. Okay, we've got to do that first. Once you draw that Lewis structure, then you're going to see if there are only two atoms or only two groups of electrons around a central atom, like the one I just showed you, that'll end up being linear. All right, we're going to practice some of these, okay? Our next rule would be 3 groups of electrons around the central atom, trigonal, okay? 4 groups around the central atom, it'll be tetrahedral. No non-binding electrons there, it's 109, okay? So these are our basic ones to start with, and now what we're going to do is we're going to take that 4 group and start taking away a leg. So for every non-binding pair of electrons, take a leg off the tetrahedron away. So that's how we started it. We take that top of that tripod away. All right, 1 pair of non-binding at the top, that's going to be our pyramid one. And 2 pair of non-binding, we're going to have our bent, like our water. Okay? So those are our rules and how we end up figuring out what something's shaped. So we're going to be able to figure out how it's shaped by drawing its Lewis structure. So let's try that. Oh, it says something about page 607. I don't know if that means in the back there is some good practice. I thought I looked it up, but I don't remember. Okay. What are the shape and bond angle of a PHCl2 molecule? Okay, so the first thing we have to do is what, according to our thing on the bottom here? First thing, determine the Lewis structure. So let's look at our chart. I think I do, yes. Thank goodness I did write this down for myself. Okay, so what do you think is going to be in the middle of this group? This is a weird one. This is different than the things I was showing you last time, right? Because we have 1, 2, 3 different things coming off, or 2 different things coming off a central molecule. The question is, which one's the central molecule? Any guesses? Let's take a look at where everything is. There's phosphorus. Where's chloride? Over there, okay. And hydrogen, is not going to be the center. Everybody understand that? Everybody agree? Hydrogen will definitely not be in the center. It only has 1 little electron to share. So now we got to figure between phosphorus and chloride, which one do you think is going to be in the middle? There's 2 chlorines. That's a big hint right there. So what's going to be in the middle? Phosphorus is going to be in the middle. Okay, so put your P in the middle. Oh, do you have a place for this in your book? To write this? Okay, put your P in the middle. And then you're going to hang your hydrogens off some legs there and some chlorine up at the top there, I think. Oh, no, I'm sorry, 2 chlorines and 1 hydrogen. So I will draw it in this little white box. Where is all right. So we're going to draw our phosphorus. We're going to have a Cl. We're going to have Cl. We're going to have an H. Now our H is done, right? It's done. How many pairs do we have about phosphorus? 1, 2, 3, 4, 5, 6. So what does it need? 2 dots. Then I have my 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Y'all see how I got that Lewis structure? Mm-hmm. I got it off the internet. I'm kidding. So you can count all those right there, right? So this is 5 points. I think I actually got it out of your book. All right. So now you can see, let's go back to our rule thing there and see what's going on. Okay. So we drew the Lewis structure. Only 2 atoms or 2 groups of atoms. So we have 3 groups of electrons around a central atom. So what do we, is that the one it's going to be? No, we actually have, this would be a 4th group. Okay. Okay, those two dots at the top. All right, but we take a leg away, right? So look at the top of phosphorus. You see there's two dots above there. So that's a group, but it's not a bond with something else. So that is going to be in our group down here. Take a leg away, one pair of non-binding. Is it pyramidal? What do y'all think? Let's do our next thing right here. There are 4 groups of electrons around the central phosphorus atom. Since one of the groups is a pair of non-binding electrons here at the top, one leg is taken away. So we look at our thing down here, one leg is taken away. 107 degrees pyramidal? Yeah. Okay, good. Good, yay for me. Got it. You see how I did that? So do you think you're going to need to practice some Lewis structures? Maybe? Yeah, okay. Well, you have some in your book to practice. Do we have some more to do here? Oh, I had something here. Oh, do the rest of 5.2 on your own. So you have like 3 more boxes there. Those are your on your own in your book, so y'all do those. I'm gonna erase this. All right, so you just got to practice those Lewis structures. Now we're at 5B. So you have stuff on the bottom of your page maybe for those on your own, or we may have some lab stuff there, I don't know. This is just a review of molecular geometry. I believe it's at the top of your page, yes? If you want to write all those down again, you can. But that's all it is. It's just that's just literally the shapes and the bond angles. Tetrahedral 109, pyramidal 107, bent 105, trigonal 120, linear 180. So you can rewrite them again. It's up to you. All right, now, this is chemistry 2. Check it out. So we know these right here. This is chemistry 1 on the top. Look at what happens down here on the bottom. Yikes. That's when we're looking at d orbitals, f orbitals, when things get really big and kind of messy, all right? So there is more complex geometry out there with these crazy angles and stuff. We don't have to worry about those right now. We're just going to worry about those top 3 right there, those few that I gave you, all right? Now, remember there are 2 types of bonds. This is all working towards something for the rest. The hard part of the module is coming up now, okay? So we know there are ionic bonds. What happens in ionic bonds?
They release and give away.
Thank you. Yes, electrons. Then there's covalent bonds. Electrons are given and received or taken, stolen or given away. Yes, those are ionic, creating ionic ions that are attracted to each other. But covalent compounds are sharing. We're going to share electrons. That's basic chemistry right there. That's Alex Trebek on Jeopardy. Okay, you got to know those. Ionic is giving and taking. Covalent is sharing. Okay. All right. So there's 2 types. Well, it turns out there are 2 kinds of covalent bonds. What? So now we got to go look at those covalent bonds, which were always a little more difficult than the ionic bonds, right? They were already a little more difficult. We didn't have those cool little crossover tricks and stuff like that. So now we're going to see something about the 2 different kinds of covalent bonds. All right, here it is. Ta-da! Covalent bonds, they're sharing electrons. There are nonpolar covalent bonds, and there are polar covalent bonds. And what is the difference? The difference is nonpolar covalent bonds are equally sharing those electrons. They're equally sharing the electrons. The polar covalent bonds are unequally sharing them. One of them is being a hog, hogging them. When we look at H2O, oxygen is stealing those electrons more often than hydrogen gets them. Therefore, H2O is polar. It's polar. These little pictures here kind of show it's all evened out here on the left side, the nonpolar. On the right, you see how one side's a little fatter and bigger because it's pulling on it's the bully, pulling on those electrons a little better, a little stronger. And our job is now, at the last part of this module, is to figure out which ones are polar and which ones are nonpolar. And then to make things a little more confusing, they call them by different things besides just polar and nonpolar. Nonpolar are also known as pure covalent. So you have to remember that. All right, so we understand the difference between polar and nonpolar, sharing equally, sharing unequally. All right, let's see what is the application of that. All right, purely covalent bonds are the same thing as nonpolar. So nonpolar equals pure covalency. So if you say I have a purely covalent molecule, you say, oh, nonpolar, nonpolar, nonpolar. That's all the information I need, okay? It's a covalent bond where they're shared equally between the atoms. So we can see right here we have a carbon and 4 hydrogens. That's our methane. What shape is that, by the way? It's got 4. Tetrahedral, right? Tetrahedral. What are those angle?
107.
I'm just going to trust you on that.
109.
109, yeah. Okay. Okay, there we are. So now you can see how if carbon is maybe pulling on those more, yes, 1, 2, 3, 4, 5, 6, 7, 8, but it's pulling on them all in all directions. All right, so it doesn't end up having polarity. Polarity, I need you to understand, when it's sharing unequally, that polarity gives part of the molecule a slight charge. Slight. We've talked about that with water a lot. When we did the water stream coming out of the cup, remember? And it bent? Remember that? Because the electrons were pulling on that polar molecule. Okay? It wouldn't work if I put methane, if I could, it's a gas. But let's say, if I put oil in there. If I put oil in there, guess what? It would not curb it, because oil is not polar. All right? It's non-polar. It is pure covalent. All right. So polar covalent bonds are shared unequally. There's our water. It's the big star of this, the one that shows it so much. So notice how, since the oxygen here on the top is pulling on those electrons more strongly than hydrogen is, I end up with this partial, that's what that little tiny delta is. That's a lowercase delta, Greek letter. Delta negative. That means I have a slight negative charge to my oxygen side of the molecule. And because those electrons are over there, I have a slightly delta positive charge on my hydrogen side of the molecule. All right, we know it's bent, we know that, right? And now we're going to see how it's even, that 105, I believe it has to do with the fact that those electrons are being pulled so strongly by that oxygen right there. So it creates what we call a slight delta charge. By the way, H2O having this polarity to it is a miracle. We should praise God every day for that, okay? Because it turns out this makes water the magic that it is. All right, it makes it where it's life on this planet. If it were not polar, water would evaporate at room temperature. Would that be good for us?
No.
We wouldn't have any liquid water on the earth. Okay, so this is beautiful. And there's a couple reasons for this. We're talking about surface tension and all those kind of things, all have to do with the polarity of water. All right, I believe. Okay, we have to remember electronegativity. I was hoping we were done with electronegativity, but we're not. We got to remember this. Do you remember what electronegativity was? More electronegative elements will pull hard on the electrons, depending on where they are on the chart. So have your chart in front of you so you can take a look at it. Depending on where they are on the chart, the higher the difference, listen, the higher the difference between the electronegativities, the better the chance that it's polar. So if we remember that electronegativity up and over, or the stronger over here like this, so the better chance for polar covalency there. Polar covalent molecules develop slight electrical charges, and nonpolar do not have any charges. Okay, so I don't know if you're supposed to write this down, but we have to remember electronegativity. It looks like that. Remember our arrows? I think we drew those, right? So we notice up here now, on this particular periodic chart of the elements, you see the numbers at the bottom of the boxes? Those are nice. I have a chart here from, this is a chart that has 2 sides to it, okay? I bought these one year for my science students, for y'all, for my chemistry kids. Then I realized there was way too much information on this. It would give you, it has even all the electron configurations are right on here. I'm like, wait a minute. And so this one has on one of these sides, it has our electronegativities. So now I could literally do the math and subtract this one from this one and see if I have a chance of polarity. Okay, so I have a guy, the guy we're going to look at now is a video of a guy named Professor Dave. We'll meet Professor Dave a couple more times this year. He's a little goofy. And then I joined kind of part way into the video. Here's how it starts. There it is. I'm an ionic bond. You know, that's James Bond if anybody doesn't know that. Okay.
Speaking of shared electrons, if the difference in electronegativity between the 2 atoms is less than about 1.7, no electrons are stolen, but instead the 2 atoms share 2 electrons. The electron from this atom feels the attraction from the other nucleus, and so does the electron from this atom. So the atoms share the 2 electrons to form a covalent bond. Covalent bonds can be polar or nonpolar. If the electronegativity difference between the atoms is not high enough to cause ionization, but is at least more than 0.5 or so, like with hydrogen and chlorine, Instead of completely stealing the electron, the chlorine will just sort of hog the electrons in the resulting covalent bond. The more electronegative atom in a polar covalent bond pulls the electron density towards itself. And as a result of the slight electron excess, we call this atom partially negative, denoted by the symbol delta minus. The atom whose electron is getting pulled away is slightly electron deficient, and therefore partially positive, or delta plus. If the electronegativity difference is less than 0.5, the covalent bond is said to be nonpolar. In a nonpolar covalent bond, the electrons are shared more or less evenly, or in the case of two atoms of the same element, precisely evenly. The atoms will have no partial charges at all. Other than strange phenomena like metallic bonding, these are the main ways atoms bind to one another. Remember that you can predict the type of bond that will form between two elements by comparing their electronegativities. If the difference is very low, less than 0.5 or so, it will be a nonpolar covalent bond where the electrons are shared evenly. If between about 0.5 and 1.7, it'll be a polar covalent bond where the electrons are shared, but one atom holds them more tightly. If above 2 or so, one atom will simply steal an electron from the other, and you'll get ions that are joined by an ionic bond.
Okay, so that's nice if you have a chart that has all those little numbers on there, and you can figure out if it's less than 0.5 or between 0.5 and 1.7, if you can do that math. But we don't have those numbers in your chart, do we? So we're going to have to figure it out in another way. But we do know where the more electronegative things are. Okay, we know where they are on our charts. They're up and over, right? Up and over. So we're going to be looking at something. So one of the things that really will help us is if we draw it. So if we draw it out like this. So here we've seen that we have, what shape is that one in? It's got three things. Yeah, which one is that?
Trigonal.
I think that's trigonal or trigonal, however you want to say that, yeah. And you can see how we have an unequal sharing here, right? So we have a polar bond of our boron, this is boron, I guess, trifluoride right here. And so we see that, I don't like the way these arrows are. They're going the right way, but this is what's pulling. The central atom is what's, I take that back. The central atom's not pulling. Okay, so they are going the right way. That's just unusually shown there. Typically, they're going inward, but on this particular one, all we need to know is that there are some delta charges. Therefore, that's a polar bond. So how do we tell? So this is the arrows I want you to understand right here. Okay, so we have let's look at this COH2 right here, the one on the left. You can see how it's got that little cross with the arrow coming at the top of it there. So what does that mean? The arrow is where the electron is going. So that electron's going toward the carbon away from the hydrogens. I kind of like the cross there shows a positive, yeah? You see the little positive right there. So I guess that's on purpose. Nobody ever mentions it, but that's what I use for it. Look at our CO2 right here. Notice how my positive charge is pulling to the left on this side, so my electron's going that way to the left, but on the other side, on the right side, the positive charge, and then going to the right. Now on this one on the right, the CO2, do you see how those arrows are pulling in the opposite directions, exactly the opposite direction from each other? So that's going to show you, those are going to cancel out. That means that one's not going to be polar because they cancel out. Does that make sense to you? Kinda? Okay. The other one, however, is just the one going that way. This one's going to probably be polar then. All right, if we can see that, okay, how do we find that? We look for those electronegativities. All right, let's try it. Here we do. This is on 5.3, page 190. Identify and label the polar bonds in NH3, which is ammonia. First, you're going to draw the Lewis structure. So we have our NH3. What's going to be in the middle? That's easy. N, right? Hydrogen's never in the middle. It's going to have the 3 H's around it. Okay, so we're going to see here. It's going to look like that with our non-bonding, our little group at the top there. So 3 bonds we're going to see here. We've got our H's and our nitrogens. We don't have to worry about this one right here, but we have these 3 bonds we need to worry about right here. So where is our nitrogen on our chart? Let's take a look. See how it's kind of to the right over there? Hydrogen's way to the left. Okay, so which one's going to be pulling more? Electronegativity. It's going to be our nitrogen. Right? So the nitrogen has a greater electronegativity because where it is on the chart, it's to the right of hydrogen, but just a little bit lower. So the arrows are going to point to nitrogen. So if I added that in there, what do I do with my marker? So I would have these little arrows going this way, pointing with a plus by the hydrogen, pointing to N, plus by the hydrogen, pointing to the N. Now see how those are not equally pulling that way, right? So we're going to see polarity here. Just got to erase those now. All right. A covalent molecule can have polar bonds but still be nonpolar. Yikes, are you kidding me? Okay, so I can figure all that out and find out that it's nonpolar overall because there's no net charge. That has to do with like that CO2 because they're equally pulling. What makes a molecule polar covalent? Sometimes polar bonds in a molecule can all work against each other and end up canceling each other out, no overall charge. That's our CO2 that I just showed you. If you draw those little arrows on there, that's how you'll know. So you have to determine the shape. So see how everything's building here. Lewis structure, shape, polarity. All right? You must have polar bonds to start with. Okay, so you have to be looking at those polar bonds, so we have to start there. So we have them here between our O2 and our C. That's interesting because look how close they are on the chart. Yeah, okay. So you can see now why they're pulling toward the oxygens, right? Because oxygen is more electronegative. See that? Okay, you see that. But they're vector addition. So here is the two arrows. I like it on the right here. It shows those arrows being opposite each other. You see? So they cancel each other out. Whereas in the one on the bottom here, the H2O, we can see that our oxygen is going to be pulling more strongly on those electrons. We know that. This way, and we're going to see how we're going to look at those two arrows right here. Not pulling equally, therefore it's polar. Okay? So you're going to have some practice problems for this. Let's try this one. Classify SiO2, that's silicon dioxide, as a polar covalent or nonpolar. First thing you're going to do is draw the Lewis structure. What do you think is in the middle? I'll give you a hint. When there's two of something, they're probably not in the middle. Okay, so the thing that's by itself. Remember we talked about that last time? The easy, the video we had about the Lewis structures made easy said put the one that's by itself in the middle. I like that. We're going to do that here. So Si goes in the middle. We're going to hang off two oxygens right there. So can y'all figure out its Lewis structure? It's going to have O and O. Okay. So it's just two on this side. We're going to be looking at some double bonds, I think, yeah? 1, 2, 3, 4, 5, 6, 7, 8. Maybe not. I think we will. Yeah. We're going to have to pull those down and make some double bonds. Remember how we did that? Pulled some of those from the oxygen. Yes? No? All right, here it is. Yeah, there are double bonds. Look at it. 1, 2, 3, 4, 5, 6, 7, 8. So when I'm counting right there, each one of those bars right there counts for 2, right? So 1, 2, 3, 4, 5, 6, 7, 8. So silicon is happy, yes. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8 on each side right there. What shape would you call that one? Yeah. So what are you guessing on the polarity of this one? Right, it's not going to be polar, is it? They're going to be canceling each other out. There are two groups of atoms around Si. It's linear. Oxygen is more electronegative, so they're going to be pulling outward. So it's pulling on silicon's electrons more strongly. They are, however, pulling exactly the opposite direction. So they are polar bonds, but it's going to be purely covalent. It's going to be a non-polar. Remember, pure covalent means non-polar. I think that's confusing. We should just call them non-polar or polar. Not the pure thing. Leave the pure thing out. All right, next is OF2. That's weird. Polar covalent or purely covalent? First, you're going to draw the Lewis structure. Okay, so let's put the O in the middle. We have the F's hanging off, right? The fluorine's hanging off. I guess that's oxygen fluoride. Yeah, so OF2. It's going to look like this. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay, that makes sense. Notice what shape it is. Bent. So that's going to give us a hint right here. If something is a shape like a bent, what are our vectors going to be doing? What are those? They're going to be kind of not canceling each other out, right? 4 groups of electrons, 1, 2, 3, 4, 2, non-paired, it's a bent molecule. Fluorine pulls very strongly. Furthermore, the asymmetry of the molecule causes there to be uneven pulling. So it's going to be polar. So Lewis structure, shape, polarity.
How do you know when you're and when it's bent?
Because of where those extra pairs are. Right there. Okay? So you want to go back to silicon. See, it didn't have any unpaired on it to cause that to bend down. Where here, we have these two guys, just like H2O, have those extra groups up there. Does that make sense, Sarah? Yeah, okay. All right. So what? Why do we care? Who cares? Do we just have to do this because your chemistry book says do it? Well, it turns out there's a practical application here to your very life. You. Okay? What it means, like dissolves like. If you're trying to get a stain out of your jeans, what is the stain? Like, for instance, grass stains. You know, grass stains. They don't, not just anything washes grass stains out, okay? Because it turns out, I believe, they're nonpolar, okay? A polar covalent compound can dissolve another covalent compound. And ionic compounds, because both types contain electrical charges. So if I need to dissolve something, if I need to clean something, then I need to use something that's like that. They always say if you're trying to get a stain out of something, use something that is of its same type. Okay, so like dissolves like. I'm not going to clean oil very well with water. You've probably noticed that. It doesn't do very well. So you think, well, how can you can clean it with another oil, but that just makes my mess bigger. So we had to come up with a trick, and the trick is to isolate the oil by putting something called soap in there. Soap, which turns it into polar, by surrounding it and turning it into a polar molecule. It surrounds it. It doesn't literally turn it into it, but it surrounds it and makes it polar. The bonds in a polar molecule allow the molecule to dissolve other polar substances. Purely covalent, that means nonpolar, can only dissolve other nonpolar covalent compounds because there are no electrical charges present. So like, it wasn't y'all, last week I think I had with one of my classes, we put water, alcohol, vinegar, olive oil, and avocado oil. We had those things, and we tried to decide which ones will mix. Well, so the water, the alcohol, and the vinegar would not mix with the oil, but the oils would mix with each other. Because guess what? They're nonpolar. Whereas trying to put the oils in the water, vinegar, alcohol wouldn't do it, but water, alcohol, and vinegar each other would dissolve. Does that make sense? Okay. So to get grass stains out of your jeans, you must use soap, because that would be a purely covalent thing that would surround it and move it away. Okay? So the water could take it away, because you're not going to use soap by itself, right? The soap and the water would be able to take that away. All right? So that is a practical application of this. What is a good application of polar versus nonpolar compounds regarding solubility? We can predict what to use to dissolve solvents. Ooh, I think that's maybe the answer you're supposed to put in that blank. We can predict what to use to dissolve solvents. And now I think we have a couple of just practice problems we're going to work on together. Some of them are asking for polarity, and some of them are just asking for their shape, apparently. All right. We're going to practice. ASCl3. 4 groups are around the central atom. We have an unpaired group of electrons right there. Therefore, it's going to be a tetrahedron, because that is a group. But this leg is missing as far as an actual bond, because these are non-binding electrons. They're influencing, but they're not bound to anything. They're going to take that away. So what's it going to do? It's going to kind of push it down a little bit, and we're going to have pyramidal with a 107-degree angle. And furthermore, looking at them on the chart, that helps us with our polarity here. I don't know if this question wasn't asking that. It's got its little cross arrow things in there. So where is arsenic versus chlorine? Oh yeah, so chlorine is more electronegative. So it's going to pull it's higher and farther to the right. So it's going to be pulling those electrons down that way, so you see how that cross and arrow thing gets put in there. And notice the directions of it. Is this a polar molecule? Yes. because it's not pulling evenly. So I should have added that in there. It's polar. This picture, by the way, I literally took with my phone from your book because I couldn't figure out how to get it anywhere the other way. And put it in. I've become so good at my new phone. It goes to my account online. I'm like, there it is, right there, in my drive. I'm becoming so savvy, or not, right? Yeah. Okay. All right. SBR2, also from your book right here. So we had to draw this. What shape is this going to be? It's a single surrounded by the 2. All right, we have 2 groups right here. This is going to be, anytime you see those 2 unpaired groups like that, remember water. Remember H2O does that. Okay, and H2O is famous for being bent, right? Remember that degree angle? Should be 105, right? And then as far as polarity goes, it didn't have that in your books. I don't know if it wasn't asking that question. Let's see. BR is 35, S, where's S? Sulfur. Oh wow, so they're really close to each other. They're probably even there. Yeah. I don't think I have those numbers. I can't do that math on that one right there. But this one wasn't asking for polarity, apparently. All right, SiCl2O, yikes, okay. So this was the Lewis structure that was drawn. Y'all might have to review how I get my double bond, right? So I would have had the extra 2 dots right here, 1, 2, 3, 4, 5, 6, 7, 8 around the O. But Si would have only had 1, 2, 3, 4, 5, 6. So that by pulling the 2 from oxygen down here to the silicon, I'd make my double bond. Y'all remember how to do that? How to make your double bond on a Lewis structure? All right, so that we had to remember how to do that. Okay, so what is the shape of this one? 3 groups around a central atom. Trigonal with a bond angle, it's supposed to say of 120 degrees. So that's just trigonal. And then I don't know about the polarity of this one. Yeah, they're all over here on the right side there, because they're covalent, yeah. All right, and Ci4, that's carbon with a bunch of iodines on it, right there. That was a tough one to find. Notice how I drew this one, where you can see it's a little 3 dimensions there. 4 groups around the central carbon, it's a tetrahedron. And I'm guessing that since, where's our iodine? Carbon. Iodine, oh, over here, okay. Once again, we'd have to do math on that one to find out its polarity. Or I'd have to tell you. Because since one is lower, the other one's to the left, but kind of evening out there. All right. That's it, y'all. Did y'all think the polar part of it was the more difficult part? I think so too. All right, so do some extra. Remember, it's at the end of the module, which is a little bit of a bummer because you're reading, you're doing really well, and then you have to finish off. So finish well on this particular module. Do those practice problems. And next week we'll have that quiz, all right?